today's session is on week 10 videos. So we'll first go through week 10 recap. So there are topics on histogram equalization, histogram modification, then AWGN filtering, local mean filtering, then impulse noise filtering, transform domain filtering, illumination compensation. So first one is histogram equalization and modification. So in order to get an idea of what is histogram, question 1 is about histogram. So match the images and the histograms and the corresponding histograms. That is the first question. So this is image A, image 1 and image 2. You have to match with histogram A and histogram B. So what would be the histogram of first image and the second image? So in the first image, you can see that there are black color and the brightest intensity levels are absent in the case of first images. So here you can see that in the x-axis you have a number of gray levels, right? So you have 0 to white color gray levels are there, and you can see that middle intensities values only we have values. So it means that some pixels are having only this many gray levels. So it doesn't have a 0 black color intensity and it doesn't have a bright color intensity. So we can say that the image is having only a gray shades only. It doesn't have black color or a white color. So we can say that image is having lesser contrast. So such histogram will be looking like this. So the histogram of image 1 will be A and histogram of image 2 will be B, because here you can see in the second image you can see there are white colored intensities values and black color values also. So there is a variation from black to white color in the case of the second histogram B. So answer for the question 1 is 1A and 2B. Then about histogram equalization and modification. So which of the following statements is true? Histogram equalization is a special case of histogram modification in which the specified histogram is uniformly distributed. So which one is the general definition, like histogram modification or histogram equalization? And the second statement is histogram modification is a special case of histogram equalization. So the answer is A. Histogram equalization is a special case of histogram modification. So histogram modification is the general histogram, where we can have an output histogram that can be of any shape, okay, and our histogram, our input histogram can be converted to a type of this output histogram. So this is known as histogram modification. But in the case of histogram equalization, that is a subset of histogram modification, where the output histogram will be a uniformly distributed histogram. So we can say that after histogram equalization, the intensities values will be like we'll get an output of a high contrast image, that is all the intensity levels will be there, or 0 intensity and the brightest intensity will be there in the image. So that is meant by histogram equalized image. But in the case of histogram modification, we can give any output histogram that can be like less contrast or high contrast. So that is up to us, okay. So the answer is A. Histogram equalization is a special case of histogram modification in which the specified histogram is uniformly distributed. Then this is the question given in class itself. The perform histogram equalization of an 8x8 image with a histogram shown in histogram as shown below. So if you have gone through the videos, you have an idea how we'll get the histogram equalization of this image. So we have an 8 by 8 image. So how many pixels will be there? 64 pixels will be there. Okay, so and here we can see that the gray levels are from 0 to 15. So 0 to 15 means we will have a 4-bit image, like every pixel will be represented using 4 bits. So 0 0 up to 1 1 1 1 means 50. So you have 16 gray levels. Okay, so the first step is, so we have this histogram of input image with us. Okay, and what is meant by this histogram? So we have 0 intensity value. So in an image of 64 pixels, 4 pixels will be having 0 color, 4 pixels will be having black color, 6 pixels will be having this gray value 1. Okay, 6 pixels somewhere will have a gray color 1, up to there are no white pixels because 15 pixel value is 0. Okay, so that is meant by this histogram. Then so the first step is we have to draw the CDF of this histogram. So we have to draw this FR of R, capital FR of R. So CDF will be accumulated version, right? So 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. Then you have to draw like this. Here you have 4, so 4. Then at 1 you have 4 plus 6 10. Then at 2 4 plus 6 plus 10 20. Then you have 29 37 43 48 52 56 etc. 64. Okay, so you have FR of R. Then okay, then you have to do histogram equalization. So your output histogram should be a uniform distribution. Okay, so you have to draw the output histogram. Then F Z of Z should be, how many colors are there? 0 to 15, 16 colors are there, 64 pixels are there. So in order to get a uniform distribution, every intensity value should occur at 4 pixels, right? So you will have a uniform distribution like this. Then you have to draw the CDF of this function, FZ of Z, that will be accumulated version, 4 8 12 16 etc. Okay, up to 15 you have to draw. Then the thing is that Z equal to FZ of inverse of FR of R. So what should you do? So for a particular pixel value 0, okay, you have to go through first FR of R. So 0's R equal to 0, whose FR of R is what? 4. Right, here, from here you can say that it is 4. Then where that 4 lies in FZ of Z? 4 lies in 0 itself. So 0 will be converted to 0 only. Okay. Then we have R equal to 1. For R equal to 1, FR of R is 10. Then where that 10 falls in FZ of Z? In between here. So you will take this 12. Then that value is at 2. So 1 will be converted to 2. Then R equal to 2. So for R equal to 2 we have 20. So 20 lies here at 4. So 2 will be converted to 4. So every pixel intensities will be converted to like 0 to 0. Every intensity value 1 will be converted to 2. Every pixel value, every intensity value 2 will be converted to 4, etc. So the output histogram will be looking like this, like 0, 1, 2, 3, 4, 5, 6, etc. 15. So in the input pixel it is 0 and the output is also 0. So at 0 we will have 4 itself. Then input pixel was 1, but the output pixel intensity is 2. So there is no color 1. Okay, there is only 2. So that output pixel occurs 10 times, right? Because in the input image 1 occurs 10 times. So here 2 occurs 10 times. So 2 occurs 10 times. Then 3 doesn't occur. Then 4 occurs. The number of times were 2 occurs. 2 occurs at 20 times. So 4 occurs 20 times, etc. At 14, 15 also will have values 4 and 4. So you can say that the input histogram is a converged one, like there is no values at 14 or 15, but the output histogram is stretched one, right? So this is S, Fs of S. So this is the output histogram. So R is somewhat transformed to S. So this is meant by histogram equalization. So the steps are clear. Then in the case of histogram modification, input histogram will be given. Along with that, one required histogram will also be given. We have to convert this histogram to this type of histogram. So instead of using uniform histogram, here at this place we will have to introduce this one, this Fz of Z. Then the steps are, you will given Fr of R. From that you have to draw CDF of the function. Then it is given. Then Fz of Z is given in the case of histogram modification, but in the case of histogram equalization it is a uniform distribution. Okay. So from that you will have to draw Fz of Z, CDF. Okay. Then using this equation, Z equal to Fz inverse of Fr of R. So for every R you have to find out Fr of R from here. Then that value where it occurs at Fz of Z, where it occurs at Fz of Z, that you have to find out. That Z is the output. So R will be converted to this is S. Then draw the output histogram. So we can say that histogram equalization and the histogram modification both are similar, but the Fz of Z is uniform in the case of histogram equalization, but in the case of histogram modification Fz of Z is the given histogram. Okay. Then comes noise filtering part. So noise filtering is also an image enhancement technique in which effect of noise should be removed. Okay. That will enhance the visual appeal of the image. So most common types of noises are AWGN, multiplicative noise, periodic noise, impulse noise and photon noise. So these noises are already explained in the videos. So we have mean filter. So this mean filtering can be used to remove this noise. So say we have an image with different noise like this. So there will be an underlying structure here, and on that structure some noise will be looking like this. So we have to remove that noise. So for that we can use mean filters. Okay. So what does mean filter do? So it is a box filter. So mean filter is a box filter where we'll have values 1 by 9, 1 by 9. Okay. In all the places we have 1 by 9 values. Then if you have a image like this, if you have a box filter like this, you will place this box filter on the image. To get the convolution. So you have to do the convolution between this box filter and the image. So we will multiply every pixel values with this mean filter and sum to get the center pixel value, and will be given here. Okay. So this is what you are going to do for a mean filter. So its equation is given like this. So the modified pixel value will be what? 1 by 9 into box filter value. Okay. So here f of q is the underlying pixel intensities. Okay. And we can say that every pixel will be having the same weightage 1 by 9, right? But we don't want that. Like the center pixel should have more weightage and the far away point should have lesser weightage, right? Because if you have an image like this, you have a pixel value here. Okay. In the case of box filter, you will add the same weight of this far away pixel to the center pixel. So the center pixel value will be the sum of 1 by 9 of the center pixel itself and 1 by 9 of a far away pixel. But we want the weightage of the center pixel more. So for that we can use weighted mean filter. Weighted mean filter, one example is Gaussian filter. Here we have that box filter won't have the same value 1 by 9 all over, but it will have a higher weightage at the center, and as we move to the edges it will have a lower weightage. Okay, that type of filter is known as Gaussian filter. So G sigma will have this equation. So it depends on the position also. Okay. Then in the case of bilateral filtering, if you have an edge like this, if you have an edge like this, if you have an edge like this, if you are using simple filters, so the neighboring pixel will also be added to the edge, and your edge will be looking like a blurred edge, right? Like this. So that we want like a sharp edge. So at the edges the averaging should not be happened. So this type of processing can be done using bilateral filter. Okay, bilateral filter means it will account the value of the pixel itself. If the value of the pixel values are very varying, like this will happen only at the image boundaries. So if the value of the pixel value fp and fq are very varying, because at this position the value of the intensities won't be changed much, right? But here the value of the intensities values are changing. So fp and fq will be very different. So this G sigma will have higher weightage in the case of same intensities values, but in the case of edges the intensities value will be very different. So G sigma will have, if this is a higher value, so this G sigma will give a lower weightage to this summation. So this is how bilateral filter works. So it is useful in the case of edges. Okay, so it won't blur the edges. So one question is here. Question 4. Which kernel is for mean filter and weighted mean filter? So mean filter kernel will be, it is simple, the mean of the pixels will be given to the center pixel. So it is mean filter and it is the weighted mean filter. So center pixel will have more weightage here if you are multiplying this with 4. Okay. Question 5. Which pair A or B could be the input and output of a bilateral filter? So what would be the answer? So bilateral filter will be used for used in the case of edges. So if an image is having more edges, if you are using any other mean filter or this weighted mean filter, this will blur the edges. But if you are using bilateral filter, it will preserve the edges, but at the same time it will remove the noise on this textureless areas. Okay. So here the noise will be removed, but it will preserve, at the same time it will preserve the edges. So A is used for bilateral filtering. Then we have non-local means filtering. So here the output of a pixel at point P will depend on the similarity of a patch at Q. So, so you have to divide the image into smaller patches, and we have to find the similarity of the of a particular patch with of the center patch with the neighboring patches, and the patches are similar, then that will give higher weightage using this Gaussian function. Okay. So this is what is done in non-local mean filtering. So here you can say, so match the images and their caption. Noisy image is this one. Then Gaussian filter is a simple filter, right? It is not a complex filter. So it will have, it will reduce the noise because noise is here, but it is reduced here. But at the same time it introduces blur at the edges. So we can say that it is a Gaussian filter output. But in the case of non-local means filter, it will compare other patches, and if they are similar, then that will be used for the weighting function. So this is the non-local means filter output. Then we have impulse noise filtering. So so a normal type of noise will be there in all over the image, right? But impulse filter is like a salt and pepper noise. It will occur at specific points. So how can we remove that impulse noises? So one thing we can use is median filter. So median filter, what does median filter do is, it will take a patch, it will take this patch, this blue patch, then in the blue patch it will take the median value of the pixel intensities. So salt and pepper noise will be, salt noise will be of higher intensity and pepper noise will be of lower intensities, but those noises won't affect the whole image pixels. So if you are taking a median value from this patch, from these 9 elements, median is what we are taking. So 0 will be here, center pixel will be here, 255 value will be here. So if you are taking median, if you are taking the median value, that median will be a clean pixel and that will be given to the center pixel. So if you are taking the median of those 9 values, noise can be, the salt and pepper like noise can be reduced. Then there are max filter and min filters are there to remove So max filter can be used to remove pepper noises. So lesser intensity values will be removed by using max filter. So we will sort the pixel values, intensities values, and the maximum value will be given to the center pixel. Then min filter can be used to remove salt noise. So it will remove higher intensity noises. Then we have alpha trimmed filter. So it is a combination of mean and median filtering. So first we have n square total number of pixels. Then we order them according to the intensities values and delete d by 2 lowest and highest value. So we have a number of intensities. We'll delete these values and these values to get remaining intensities values. Then we'll find the average of those intensities values. So here you can say that it is a combination of mean and median filtering. Then you have weighted median filtering. In the case of weighted median filtering, you will repeat values. So Wi delta xi is repeated Wi times. So instead of just using only one intensity value, if the weight is 3, that will be repeated 3 times, and after that we will find the median. So that is known as weighted median filtering. Then center weighted median filter is, so center pixel will be weighted for a particular weight. Then question 7, find the center weighted median filter output with a weight of W equal to 3. So center weighted median filter Y is equal to median of x1, x2, etc. and the center pixel will be weighted by WC. So we have these many pixels. So first you will sort them like 5, 14, 17, 29, 38, 42, 66, 91, 111. Then what is the center pixel? 66 here, right? So you have a weight 3. So you will repeat 66 3 times. So you will write it as 5, 14, 17, 20. So if it is a simple median filter, what will be the output? So this is the median of these values, right? 38 is the median. So that will be given to the center pixel. But if you are using a center weighted median filter with a weight 3, you will repeat this 66, that is the center pixel, 3 times. Then we have to find out the median. So here the median is here only. This 42 is the median, right? So 42 is the median. So if you are finding center weighted median filter output, we will give the 42 as the output to the center pixel. So until now we did filtering in the spatial domain itself, but if you have transform domain filtering also. For that we will convert the image to transform domain first. So you have an image like this using any unitary transform, like we have DFT. So we can use the Kronecker product to find the 2D kernel to convert that to VKL, or you can use AUA transpose. So at last you will find the kernel for a transform like this. Then at every position we will apply some filtering. So we have a mask like this GKL that will be multiplied with this input. So these two will have same dimension. So that will be multiplied with this to get V dash KL, and that will be given to the inverse transform function to get the filtered output. So this is similar to like convolution with a simple kernel. So here it is the product in transform domain. So we have to use the Fourier transform of the kernel that we used in the spatial domain. Okay. Then we have SVD filtering, singular value decomposition. So here the original S can be written like this, and we have R singular values, but we can filter the image by using less number of singular values. So we will use only P singular values like this. So that will be having lesser information than the original image. Then we have notch filtering that can be applied for a periodic noise. So if we are aware that an input image will be having a single tone noise like a 50 Hz noise, then we can use a notch filter to remove that noise. Okay, notch filter will be looking like this. So that will remove that frequency only. Then we have Fourier based filtering. So we have ideal low pass filter and Gaussian low pass filter. So low pass filter will be looking like this. So it will be a 3D structure. Gaussian low pass filter will be having a bell structure. Question 8. So what type of filtering can be used in this type of noise shown in the figure? So here you can say that it is a plus sign noise. So it is having a single tone frequency. So that should be filtered out. So we have to use a notch filter like this. So we'll get this filtered output. So filtering is notch filter. Next question is, an input image is filtered using a Gaussian low pass filter of size 35 by 35 sigma 4 and 10. So which output correspond to higher sigma? So standard deviation is less means this type of structure, standard deviation high means this type of structure, right? So this red one is having more weightage to the far away pixels also. So if we have 10 here at the center, the red one will be having like 8, here 5, but the blue one will have if we have 10 at the center, here it will have 3 only, it will have only 1. So the far away pixels will be having lesser weightage, but the center pixel will be having more weightage. But in the case of red one, which is having higher sigma, far away pixel having higher weightage. So the output of a filter with higher sigma will be a blurred version. Like a far away pixel will also be accommodated to a particular pixel. So this 10 sigma value will be looking like this. This 4 sigma value will be looking like this. So here it is having higher sigma. Then the last topic is illumination compensation. It is used for removing this non-uniform illuminated images. Like you have light here, but as we go through this set, the illumination is lesser. So such type of illumination, non-uniform illumination can be removed using homomorphic filtering. So here first of all you have to find out this natural logarithm of the input image, because the input image can be represented using the product of reflectance and luminance function. Then after that only you can use this Fourier transform to separate them then you can apply a high pass filter, because this illumination variation is a low pass, is having a low pass nature. It is a slowly varying, so we can use a high pass filter to remove that illumination variation. So after applying this filter, you can find the inverse transform to get the original image back. So that will have a illumination compensated image. So which filtering would be used to filter such an input image 1 to get the filtered output image 2? So here you can see in most of the images with light tone will have such an output, right? So here you will have a higher illumination. As we go through this set, so it will have lesser illumination. So if you are using homomorphic filtering, you will get an output like this. So that's all about today's presentation. Then lab assignment 10 is on k-means clustering. First you have to take these centroids for the initialization. Then you have to run for 5 iterations. Then the next case you have to take random initialization and you have to run for 30 iteration. And here you have to find the clustered image and cost, and the plot the output, clustered output, and the cost is maximum and minimum. You can say that you can find that the output at the cost minimum will be a good image, good clustered image. So this is all about week 10 videos. So any doubt? So if you don't have any doubt, we'll stop. Thank you.